So I am Jez Humble. I am a site reliability engineer working at Google Cloud. Who's heard of site reliability engineering before? Okay, quite a lot of you, not everyone. So site reliability engineering, we don't do traditional ops at Google. What we do is we get engineers and have them work in ops. And the idea is rather than operations being kind of like clicking on stuff and manual work, we work to automate things and make sure that as the platform scales, we don't need to scale the size of the team that manages and operates that platform. So we apply software engineering solutions to the problem of running and maintaining platforms in production. I am a tech lead on the serverless SRE team, where ironically I manage a very large number of servers. The serverless platform is Google App Engine, Cloud Run, Cloud Function. So Google App Engine was a cloud service before Google Cloud existed. So it was, predated Google Cloud. It's still running, still a great platform, and I have a lot of fun working on it. So I'm going to start by saying that what I'm presenting today is the work of a lot of people. You can see here, these are all my colleagues on the serverless SRE team, which is in San Francisco and London. So we are all on call for the platform. We have on-call rotations. I'm on the San Francisco side. We are on call from 10 a.m. to 10 p.m. and then the pager gets handed over to the London team, 6 a.m. London time to 6 p.m. London time, and then the pager gets handed back to San Francisco. So these are all the people that are on call. The work that I'm talking about today, the ideas were invented by the Kraken team, led by Narayan Desai, and a whole bunch of other people from inside and outside Google contributed to it. So all that to say, I work with a lot of really great, smart people who I'm proud to work with, and what I'm presenting today is the work of a lot of people, not me. So the serverless platform is really cool. You can deploy containers, you can deploy codes from the command line, and we take care of scaling and infrastructure for you so you don't have to. It scales down to 0 and up to thousands of instances in seconds, which is really cool. But basically what we're doing with that is we're giving our customers the ability to apply severe load to our platform. So that can be quite painful. We have some very big customers, and some of those customers do things that involve a sudden arrival of an extremely large amount of QPS on our platform. So for example, major sporting events, you could have millions of people tuning in to watch a match at the same time, and that's going to instantaneously spike up QPS to very high levels on our platform. So we definitely feel that. We can see that happening, we can feel it. It's a shared platform, it's an amazing platform, but that has an effect on it. Despite that, it works really well. But not to say there aren't issues. So I'm just going to briefly describe how the platform works at a very high level. So when you deploy an app, it's the control plane that takes care of taking that app and getting it running on the data plane and managing the life cycle of that app. So every time you deploy an app, that creates a new version, and you can split traffic between the current version and old versions and migrate traffic and so forth. And it's the data plane that does the serving. So we have multiple regions. Those regions are isolated from each other. Each region has a number of cells, which are independent data centers that your app will run on within that region. And then when a user sends a request to your app, that goes firstly through a bunch of networking stuff near the user, which could be in a completely different part of the world from the app which is serving that request. So there's a networking layer here which works out where that request is going to be served, forwards it to another networking component in the same region that the app is going to serve your request from, and then it sends your requests to an instance of your app which is running on an app server. An app server is a job that runs on Borg, our compute infrastructure, which hosts large numbers of instances, and there's large numbers of app servers running in every cell. This is obviously not to scale. There's a huge amount of stuff going on here. But at a high level, this is kind of what it looks like. This networking stuff near your app, in fact, all of this stuff, but in particular, we care about this networking component in the region, emits a large amount of metadata, a large number of metrics. So one of the things that we're going to be talking about later, we capture timestamps for every request as it goes through the stack. So we capture a timestamp for when your request hits this part of the stack. We capture the timestamp of when we start negotiating to work out which app server is going to serve your request. We capture the timestamp of when your request gets forwarded to the app server, when your code starts executing, when your code finishes executing, when it sends the request back to the networking layer, and when it exits the networking layer to send the request back to you. So that metadata and a whole bunch of other metadata firstly goes into logs. So we have amazing structured logs at Google. It's not just a timestamp and a string, it's a timestamp and a ton of protos that are stuck into that log entry. And it all goes into a big data warehouse, and you can query it with SQL. It's pretty amazing. And that metadata also goes to our in-memory global time series data store called Monarch. So Monarch stores this data as well. And Monarch is where we get all the data we use for our monitoring and observability platform when we're running stuff in prod. So who here works in platform engineering? Who's run Kubernetes or something like that? Okay. Have you ever had this experience where one of your customers is like, hey, my app's slow? Anyone had that? And how do you feel about that when that happens? So that's about 25% of the audience. So when that happens, I'm like, oh my God. Because it's really hard to work out what's going on. One possibility is that your customer changed some code and caused a problem. And that's the cause of the problem. They changed their code, they changed some config, something like that. But it could be a ton of other things. Any reasonable app has a whole bunch of dependencies, and those dependencies might be running slowly for some reason. There could be some problem with that. You might call out to a database, you might call out to some other service, and that could be behaving differently from usual. There could be a change in the pattern of the traffic to an app. And apps often behave non-linearly. If you go above a certain number of QPS, you might run out of memory on your machine, and then it might just grind to a halt. So there's kind of non-linear effects with traffic patterns to your app, or to the platform, or to some networking layer somewhere. We make changes to the platform all the time. We're always deploying new changes to the platform. There could be a config change somewhere in Google that affects one of our dependencies in some way. That could change something. Sometimes, although it's a very robust platform, if there's a huge number of QPS that comes into a particular app, that might cause problems for other app servers running, for other instances running on the same app server, or there might be other contention of resources somewhere else in the stack, and that can cause problems. Denial of service attacks, we get those. We have very robust infrastructure in place to deal with denial of service attacks, but it definitely can have noisy neighbor issues. Sometimes, if a particular clone gets a big hit of QPS, that can consume a lot of resources on that app server, and the bin packing of clones into app servers can become suboptimal, and we might need to move stuff around. So there's like a ton of stuff that can happen. And trying to work out which of those things is causing your app to be slow is not a trivial task. It's going to take a lot of debugging and understanding unless it's something obvious. And SRE are basically the people who get called when it's not something obvious. So you know you're in for a long night. So, you know, if something's really badly wrong, you know, people obviously will say, well, is it us or is it Google? And if you get a customer ticket from someone, you know, if it's just one ticket, you're like, well, it's probably, you know, some configuration change or something that they've made to their app. But when you start getting tickets from a whole bunch of customers, at that point you start to think, well, maybe it's not an individual customer problem. Maybe there's something going on with the platform. And what you would like to do is find out before customers. You don't want customers telling you there's a problem with your system. You want to know there's a problem so that when the customer requests come in, you can say, okay, we know what's going on here, it's this thing. Or we don't know what's going on here, so it's probably not us. Or at least we need to do some more investigation to find out if it's us or not. So when you get a whole bunch of customer tickets or pages, you want to know, you know, what's changed in the behavior of the system as a whole from a customer perspective. So from a customer point of view, what's changed. The problem is with, you know, my app is slow, we're looking at latency, right? And latency on a platform is dominated by the behavior of the app. So I actually went and ran some stats on this. So this is like the end-to-end latency for requests to customer apps. And there's, you know, this is a logarithmic scale. So the biggest bucket of request latencies is in the 1 second to 10 second range here. And there's like a whole bunch of buckets where the latency is much smaller. And then there's this bucket from 10 seconds to 100 seconds, and then it drops off but doesn't go to 0. So you can see in a normal operation of the platform, we're talking about 5 orders of magnitude in terms of request latency for an app. And that's normal behavior. Some apps, they're doing something that's very computationally expensive, and it takes them several seconds to process a request, and that's expected behavior. So you don't know. This is really hard to manage. Where do you set? Typically, when you're thinking about the behavior of the platform, we use SLOs a lot, service level objectives. And service level objectives for error rates are reasonably straightforward conceptually. But where would you set the SLO for latency? Well, you can't. There's no good latency here. If my app takes 100 milliseconds to respond and I set the SLO at 900 milliseconds, obviously that's useless. So SLOs are problematic in this context. So what we've traditionally done is we've taken a part of that end-to-end latency and established an SLO for that. So what we look at, the first graph we look at is request delivery latency. And that's the latency from when the request hits the networking stack in the cell that the request will be served from to the time that an app is actually starting to serve that request. And that we can establish a latency SLO for. And you can see this is one of the graphs that we look at, and what this is showing is these different colors are different cells within the region, and we can look at the number of projects for which the latency is above the threshold that we've established as the SLO. So we've got a threshold limit, and we can see that there's kind of this noise floor here of about 0 to 5 apps where the request delivery latency is under the threshold, is a bit over the threshold, and then it kind of spikes here. And here's where you would expect, for example, maybe there's a networking component somewhere or a networking job somewhere that's got overloaded, or if an app server somewhere has got overloaded, maybe that's what's going on here. So it gives you some clue at what the problem is. But it's not going to catch issues where there's an increase in latency in some other phase. For example, calling out to a dependency or during clone execution, if there's a problem, that won't get caught by this. So there's a lot of problems that can occur where this graph isn't going to move and isn't going to tell you that's a problem. And because it doesn't catch those problems, we can't measure the true customer impact of something going wrong on the platform. And more importantly, it doesn't actually represent the customer experience in terms of the end-to-end latency from when a user request hits the platform to when it goes back. So it's something, but it's not really good enough. What we actually want is a metric that represents the customer experience. We want it to be combinable across projects, across cells, and across regions. We want to use it to detect anomalies that potentially can impact multiple customers. So things that are going to be to tell us whether it's a platform issue or just a customer issue. And if it's a platform issue, is it an issue with which part of the platform it's an issue with, and how many people are being impacted by that? We want something that's computationally cheap. We get an extremely large number of QPS, as you can imagine, and we want to be able to get the data on what the impact is in near real time. And we want it to be principle-based. So, that request delivery latency, we've chosen a number for that request delivery latency. That's fundamentally empirically determined. It's not something that's principle-based, and the SLO we choose is empirical as well. So what principles do we care about in terms of the reliability of the platform? Well, there's 3 things fundamentally that we care about. Firstly, is my service available? Is it there when I need it? Secondly, how effectively is the work being performed by the platform? Is it happening in a reasonable amount of time? And then thirdly, is the service correct? Is it behaving in the way that customers expect it to behave? And there's standard techniques that we use to measure those things. So for availability, you might count, for example, the error ratio, the ratio of failed requests to normal requests. And if that goes above a certain amount, we might say that the service is not fully available. For performance, what we often do is we have probers. So probers are apps that behave in, that exercise a relatively simple workflow that's predictable and has a predictable latency. And so we monitor, for example, the P99 latency of the prober apps and alert if that goes below a certain threshold. And then for correctness, we're very big on tests, automated testing in Google. Every time a developer commits some code, they have to commit a test as well to show that that code behaves according to expectations. So we have a ton of automated tests. We run an extremely large number of automated tests continuously, and developers get fast feedback if those tests are failing. So we've got great test coverage, and we do canary analysis when we roll out new binaries or new versions of binaries to make sure that we're not impacting customer metrics that we care about. But even with all this stuff, there's more we can do, and there's problems with those existing things. So for example, there's an error. Is it an error that's a user error, or is it an error caused by something going wrong in the platform? Well, we've got a pretty good idea most of the time, but there can definitely be places where we've said it's a platform error, where it's a customer error, or vice versa, because fundamentally determining what's an error or not is subjective. It's something that we decide. There's no platonic ideal of an error. It's fundamentally part of the platform design to determine what's an error and what's not, and what's a user error and what's not. So there's always some ambiguity there. There's deadlines, things can time out without giving an error, but there can be a problem. Sometimes there's malformed requests which cause unexpected behavior, and then people implement retries, and then when you retry in the face of an error, that can magnify errors. So availability, it's not as simple as just putting an SLO on something and calling it done. We do have an enormous number of SLOs. There's one service in Google that has like 250,000 SLOs, and that has its own problem. Trying to work out when those SLOs are out of bounds and when they are, what's actually wrong, is a problem in its own right. With performance, we have these probers, but SLOs tend to be workload dependent, and often the probers are narrow. They're just testing one particular journey through the platform. The platform provides an awful lot of functionality. You're not going to write probers that can possibly test all the different functionality and the interactions between those functionalities. So the probers are narrow in terms of the actual functionality they're testing, and you're not going to find all the problems by doing that. And in terms of correctness, we've got great test coverage, but production platforms, their geometry is different, the traffic going through it is different, the dependencies, you're going to have prod versions of dependencies, and so you're never going to find all the problems with automated testing, and hope is not the strategy, of course. So what can we do? From the point of view of the operator of a platform, basically what you have is events. And in the case of the serverless platform, these events are requests. And you can see, this is the latency on the y-axis, and this is time. So fundamentally, what we're seeing come in to the platform is a whole bunch of events. But you can't really make sense out of this. Like, you can't look at this or even analyze this and say whether it looks normal or not. But from a customer perspective, it normally is pretty obvious whether something's okay or not. A particular customer workload, which in our case is a version of an app that's deployed, will typically have pretty predictable behavior. It'll have something that you can look at and say that looks good or it doesn't. And certainly most customers know what looks good and what doesn't. And fundamentally, what you want as a customer is that my app behaves the same way today as it did yesterday. So a customer is expecting, whatever the performance is, I want it to stay the same. And if it changes, I'm going to send you a ticket. So the customer expectation is, this is how our application performs, and I want it to continue behaving in the same way. And so when you break it down to the individual workloads, we have this idea of reliability, which is actually that the individual workloads should perform in the same way over time. And we can give this a statistical meaning. So if you take an individual workload and you plot that workload in terms of the latency on the x-axis and the number of requests on the y-axis, this is a log normal distribution. And you can see this is a pretty good fit for the log normal distribution. And what we're looking for statistically in terms of reliability is that this distribution should stay the same over time. The workload should continue to behave the same way tomorrow as it did today. That is to say that the distribution of latencies should continue to be the same over time. And in statistics, this is a characteristic called stationarity. So what we're looking for is stationarity of workloads, basically. That's what's going to tell us that everything's okay. And so armed with this concept of stationarity, we can then go on and define reliability in a way that we can actually use to fulfill those goals that I talked about earlier, using what's called the 2 sigma technique. So it'll become clear why it's called the 2 sigma technique in just a minute. Our hypothesis, as we've said, is that workloads that are self-similar, so workloads that are well-defined, should have consistent performance over time. What we're going to do is we're going to take all our workloads on the platform and partition them into cohorts, where a cohort is something which is going to be self-similar over time. And then we're going to build baselines for each of those cohorts. So for each workload, each cohort, we're going to determine a baseline, which is basically we're going to model the distribution that we care about. And then for every new event that comes in, we can look at that event, compare it to the distribution, and see whether or not, or to what extent it's anomalous, and basically test for stationarity of our new incoming data for requests versus the established baseline of its past behavior. And then the result is that we end up with a set of events with predicted likelihoods. What's the probability of this request having this latency compared to the baseline? And we can create a time series of that, where the time series is showing you for every request to what extent it's a deviation from the expected performance of that workload. How do we do this in practice? Well, there's two pieces to it. Firstly, we've got to establish the baselines, the model. So what we do here is we have a batch process that looks at historical service data and partitions it into cohorts. On the serverless platform, those cohorts are app versions. So every app version we deploy, we create a baseline for. This technique was developed actually not in serverless. It was developed by the BigQuery team. BigQuery is Google Cloud's data warehouse platform. And so actually they're looking at basically SQL requests. You send SQL in, you get query results back. So they're using it. It was invented to deal with a completely different domain, and it works great there. And the cohorts there are not the same. I'll talk a little bit about that later. But for the app server platform, the cohorts are basically app versions. That's what we expect to be self-similar over time. And then for each workload, we try and fit a distribution to it. This is showing a normal distribution. In practice, we actually use log normal, but you can see, here's a workload in yellow where you can fit a normal distribution pretty well to it. This green one is less good, and then this red one is a bimodal distribution, and that's not going to fit a normal curve at all. And that's what we find in practice. We find that for the serverless platform, about 50% of our workloads can be modeled with a log normal curve, and then the other 50% we reject because they're not a good fit. We can't fit a log normal curve to that distribution very well. And then what we do is we store the parameters of the distribution in a database along with a cohort identifier. So every cohort has an identifier, and we store what's the mean, what's the standard deviation, basically, in a database. So that's our baselines. Then for every request that comes in, when the request is complete, the networking stack emits those metrics that we care about, and we grab the end-to-end latency for that request, and we compare it against the baseline for that cohort, and we compute what's called a Z-score. So a Z-score is essentially how many standard deviations away from the mean is that request's latency. And this is like, if you were falling asleep, this is the point to wake up and pay attention, because it's by computing the Z-score that we can actually get something which is normalized across all the different workloads. And we can get basically a graph of Z-scores over time. And so what we expect is the Z-scores should maintain the same shape across projects, across cells, across regions, because the Z-scores should follow a normal distribution. That's what we're expecting. So this is the technique by which we take all this stuff and we normalize it into a graph where we can see for every request, how far is this request away from what we expect? And is it an outlier? And what proportion of our requests are actually outliers? And we can use this to take that intent, which is app dependent, and turn it to something where the intent is not app dependent, and we can combine that, and we can aggregate it, and we can calculate across the platform as a whole how it's behaving. So that's kind of the important bit. So that is pretty computationally cheap. And then how do we turn this into a data product that we can actually use for monitoring and alerting and performance management purposes? Well, here's what we do. We aggregate those Z-scores across workloads. And then what we look at is the fraction of requests where the Z-score is above 2, so more than 2 standard deviations away from what we expect from the mean. So any of you who's familiar with science, you might know that 5 sigma is the the threshold for something to be established as scientific, as valid in the context of science. But that's something very unlikely. For a platform, we're not looking for extremely unlikely black swan events. We're looking for something which is abnormal, which might indicate that something's wrong, that's going to give us a good prediction that customers are going to start sending us tickets. And what we found empirically is that 2 sigma is a good cutoff for that. So what we look at is the fraction of requests that we get that are above 2 sigma from the mean. And we expect, based on the statistics of a normal distribution, that that will be about 2 to 5% of requests. That's what a normal distribution is. When that number goes above 10%, basically we know there's a problem. We're expecting that 2 to 5% of requests will be 2 sigma away or less away from the mean. When that starts going above 10%, we know there's a problem. And again, we can aggregate this across a cell so we can see when a cell is starting to regress and there's some kind of performance regression in the cell. And so detection is based on the fraction of workloads that are exhibiting a regression. So, what data products, what alerting and monitoring do we actually create based on this? Well, the main data product that we create from this is a graph which creates a distribution across all the different projects running in a region. So we take all the projects in the region and we stack them up into a distribution. And typically we use like a 15-minute window for that. And so there's a lot of services that are low QPS, and so the Z-score is going to be either 0 or 1. And so we stack all the projects within a particular cell up and calculate the median Z-score, and actually a bunch of other different parts of the distribution as well. So what you can see here is the first graph that you look at when you get an alert. And what this shows is that 50% of projects are experiencing J-scores of at least 8. What does that mean? So J-scores of at least 8 means that at least 8% of requests for that project are more than 2 sigma above mean. So that's, it's not horrible, but it's definitely above the 2 to 5% that we're expecting. So if 50% of the projects are experiencing a J-score of at least 8, that's a sign that 50% of our customers are experiencing something that they might notice is a regression. And then we also have a 30% line as well here. So 30% of projects are experiencing J-scores of at least 30. So this is the J-score, the anomaly percentage, the percentage of requests that are more than 2 sigma away from the mean. And so like if 30% of customers are experiencing a J-score where 30% of requests are deviating more than 2 sigma from the mean, that like people can see that, people can spot that, and we know there's a problem. So it's very easy to see when there's a problem. And again, this is end-to-end for requests. So it's an accurate reflection of the customer experience. And then the second thing we want to determine, is there a problem? What's the impact of that problem? So the next graph that we have is this one. And what this is showing you is the number of projects where the J-score is above 10, which means the number of projects where the percentage of requests 2 sigma or more above mean is 10% or more. So that gives you can look at that and you can immediately see the number of projects that are impacted by that. So that's the second piece of information I need as an on-caller to determine that there's an incident that I need to respond to and calculate the severity of that incident so we can decide if we're going to externalize it and tell other people or if we're going to just deal with it on a per customer basis. So very easy to see at a glance. Firstly, is this a real problem? Is it a problem with the platform? Secondly, how many customers are impacted by this? Do I need to escalate this? So at this point, people normally have a lot of questions because I've used a lot of stats words. So I'm going to try and head them off a little bit. Firstly, do performance metrics actually follow normal distributions, Jez? No. You're always fitting a curve, and so the curve's never going to be a perfect fit. Actually, we use log normal distributions, as I said earlier. So log normal distribution, I showed you that earlier. And that gives you a better variety of fits. We can actually fit about 50% of our workloads using a log normal distribution. Do we know if the approximations hold? Well, we test that. We use K-stats, in fact, to test the extent to which the curve fits the actual distribution. And we reject baselines if the case stats don't fit well. So we have a threshold that we use for that, and as I say, about 50% of our workloads meet statistical test for whether the distribution fits the actual behavior. How do you define cohorts? Well, in the serverless platform, it's pretty straightforward. A cohort is an app version. Now, you could get more sophisticated than that because different paths within an app might have different behaviors. In practice, that doesn't seem to be a problem in terms of actually the use cases that we use these metrics for. It works fine. For BigQuery, they use something different. They have different features, and they calculate like a cross-product of features to define cohorts. So depending on your application of this process, you're going to define cohorts differently. But that's one of the first things you've got to work out when you use this technique is how are we going to define our cohorts. But for App Server, it's pretty straightforward. And then how do we deal with singleton or infrequent workloads? Well, the answer to that is twofold. Firstly, if you have low QPS, then it's quite hard to actually fit a distribution and be confident that that distribution is a good fit because it will be underdetermined by the data. But also, more practically, if someone's not sending a lot of QPS, they probably don't have very strong expectations about the behavior of it. So we don't care about that. If we're getting less than 30 requests to a particular app version over the 1 month period we baseline over, we just don't bother baselining that, or we don't use the baseline. So if it's infrequent, probably the customer doesn't have strong expectations about the behavior, and so we don't care about it. And then obviously you're like, okay, Jez, that's a lot of words. Does this really work? So the next thing we do is we go and do a whole bunch of backtesting. So we go over like the last 3-4 months of incidents, and we go and look and see, could we find a signal in our data from the 2 sigma process that shows this problem occurring? And actually we find it's a really good fit, which is why we're using it, because it works. So this is the graph that we use traditionally for request delivery latency, that metric that we use, which is the latency from when it hits the networking layer in the cell to when it hits your app. And we have 90% for 90% of projects, 95%, 99%. And you can see here, this is a regression that's hitting, that's taking us below SLO for 99% of projects. So that's like that's the problem that we would care about. This is fine-tuned, obviously, because we have a parameter for what the SLO is. We've got these different things that we're looking at. But this isn't fine-tuned at all. This is just like throw the data at the thing, and it shows very clearly that there's a problem. So it's super easy to see problems without any fine-tuning of the parameters of the model. It's just very, very clear. And we found that the signal that came, I love it when this happens. You're like doing a lot of stats and a lot of programming, and then you're like, oh, this really works. Yay. So that was very satisfying when we went through all the incidents, and we could see this really clear signal in the data that we were producing that matched up with the data that had been gathered from all the incidents in the course of investigating those incidents. So it works really well, actually, which is great, which is why I'm here. There are limitations. Firstly, I had to explain a lot of stats words. Who in this audience had heard of Z-scores before and was like, oh, Jez, you're using Z-scores? Well, actually, okay, you're my people, amazing. About half of you, great. So, if you understand Z-scores and J-scores, it's going to be a fairly simple journey for you. But if you don't know what those things are, then there's a bunch of stats words you have to learn. And then when you see that graph, you have to do a bunch of thinking in your head, which is not normally the first thing that you want to do when you're in the middle of an incident. So that's an issue. But in practice, we found with a bit of training that people get it, and it's pretty easy to grok. We get about 40 to 60% of coverage based on the fit of the curves and QPS. And we find that's actually absolutely fine. We have some services that have a much lower level of coverage of around 5%, which is what we got when we started using it with just a normal distribution instead. And in practice, you can still discover platform regressions just fine using a much lower coverage. 40 to 60% is great. This implementation doesn't tell you why there's a problem, it just tells you that's a problem. In the context of operability, this is actually fine. This is called symptom-based alerting, and that's actually better than cause-based alerting. We have a lot of cause-based alerts, and the problem with them is they're noisy. and you get a lot of false positives because yes, this thing may have gone wrong, but what you actually care about is, did it have a customer impact? And so you then have to go and hunt, did this have a customer impact? How do we measure the customer impact? Is this the actual cause of that customer impact or is it not? So they're noisy, they're problematic. We try and get rid of cause-based alerts in favor of symptom-based alerts. And this is an amazing symptom-based alert because it's reflecting the customer experience. And as you can see, we can very easily determine the impact on customers. So that's our application, but actually this has a ton of other applications. So the BigQuery team actually use this not just to diagnose problems, but also not only to detect problems, but also to diagnose problems. So the total time for a BigQuery request, you can split into queuing time versus execution time, and you can take the execution time and split that into I/O time and compute time and so forth. And what they actually do is they calculate the latencies of those individual phases and then chuck them into exactly the same engine. And so here's an example of something from one of the BigQuery cells where you can actually see there's this actually multi-day regression of performance. And then they've split that. This is I/O time. Whenever you see a square wave on a graph in production, that's terrifying. But you can see very clearly that this regression is dominated by I/O time. So in that situation, okay, it's the I/O that's a problem. And what they were able to do is, and this is something you can do in a so all Google Cloud services within a region are served out of multiple cells. So what you do is you just drain this cell so that you're not serving from this cell because this I/O problem was limited to a single cell. So you drain the cell to mitigate it while you work to resolve the problem. So you can definitely use this technique for diagnosis as well. And there's a lot of work being done at the moment to basically look for correlations. So here are all the dependencies. Let's find correlations in the dependencies. What you're trying to do fundamentally with a distributed system is decorrelate everything. That's the purpose of a distributed system, is to decorrelate things so you remove single points of failure. So anytime you see correlations, that's normally a bad sign. That's a sign that your distributed system is not doing what it's supposed to do. So correlations are actually very useful to know about when you're trying to diagnose a problem in production. We have an experiments framework in Google that we use to push out new features, and you can actually use this for looking at experiments and doing A/B testing for experiments. You can look at the impact of an experiment on cohorts and see if it shifts the things you care about, the behavior that you care about with an A/B test as well. So that's something we've been using it for and investigating as well. So that to say, there's a ton of different applications for this that we're only really scratching the surface of right now. So just to sum up, we have this technique. We can use it to reliably detect and measure the impact of platform regressions and know if we have a platform problem versus a customer problem and work out the severity of that so we know kind of what level of action we need to take about it. Fundamentally, the model of reliability we're using, reliability is a shared property between customer and service, and customers know what they expect. And what we want to do is be able to model customer expectation and make sure that that thing behaves the same way over time. That's fundamentally the property we care about, and that's hence what we're modeling using this technique. And the key thing is that transformation of latencies into Z-scores so that we can combine those Z-scores and aggregate them across aggregation levels that we care about, such as projects and cells and regions. And actually, we use the number of minutes for which the J-score for a cell as a whole is above 10% as a measure of, we call that metric overloaded minutes, and we use that as a measure of the reliability, as one of the measurements of the reliability of the platform as a whole. What customers care about fundamentally is variability. Like, is this thing staying the same or is it not? Which is what we're measuring. And if you extend this technique and apply it to a bunch of different things within the platform, you can look at decorrelation and detect decorrelation, which is often a good way of looking for causes of problems. This two-sigma method, we think there's actually a ton of applications of this. We think it's very widely applicable. I'm not going to go through all of this now because I want to leave some time for questions, but fundamentally what we can do is we can look for invariance of the system. We can look for things that we expect to stay the same, where we expect the distribution to be stationary over time. Any characteristic of your system that is like that, where we expect the behavior to stay the same and we can model it statistically and look for stationarity, you can use this technique to model that. So we think it's very widely applicable and very powerful. And we've shown that there's a way to implement it that's computationally relatively cheap and scales up to very high QPS, and that we can use at the platform level. There's a talk by Narayan Desai and Brent Bryan, who are two of the creators of this idea from SREcon last year, and you should go and check that out if you want to know more. I work at Google. We have a whole bunch of books that you can get for free by going to sre.google/resources to find out more. That's it.